This is number 2 of the Thermo review. So let's read the question first. The standard free energy change, delta G, for the reaction above is negative 801 kilojoules. So they're giving us the free energy. We know that it's a spontaneous reaction. So let's keep that in mind. We might need it a little bit later. A says use the table of bond dissociation energies to find delta H. So they don't want us to do anything with delta G just yet. They just want us to calculate delta H using bond enthalpies. So remember, these are bond enthalpies. They are not delta H's of formation. We are not going to do products minus reactants here. Instead, we're going to make a list of what bonds need to be broken and what bonds need to be formed, and we're going to add up the total amount of energy it takes that we have to put in and subtract it from the amount of energy that we're going to get back afterwards. You remember, the key to these is definitely make sure that you know the Lewis structures of each one of these. It's always a good idea to draw out the Lewis structure of all of your reactants and your products. I did them up here, and a lot of these we've already seen before, so you may already remember them. Oops, I forgot a couple electrons there. But in any case, the important thing is that CO2 does have a double bond, O2 has a double bond, and you can see that they've given us that information in the table. Now we just have to decide which bonds are broken. So I'm going to write down the carbon-hydrogen bonds and the oxygen-oxygen double bond. So I've listed that we broke in the methane, we broke 4 CH bonds, and I got the energy it would take to do that. There's an OO double bond, but there's 2 molecules, so we do 495 times 2, add those up, and this is the amount of energy that we would need to break all those bonds. So that's endothermic, that's how much we'd have to put in. We get some energy back when we form the CO double bonds. Each one of these molecules has 2. There's only 1 molecule, so we only have to do times 2. The water has OH bonds, and there's 2 water molecules, each having 2 bonds, so times 4. And then we add that up. This is how much energy we get back. So this is going to be a reaction that should be favorable as far as heat goes anyway, because when we subtract these two, we're going to get negative 800 kilojoules. So definitely an exothermic reaction. And that's all there is to it. All right, let's look at B. So in B, they want to know how many grams of methane must react with excess oxygen in order to release this much heat. Well, in part A, we found out that if we use 1 mole of methane, we will give off 800 kilojoules of heat. So this is one where we're going to need an energy conversion factor. 1 mole of methane is equal to negative 800 kilojoules per mole. From here, it's just a unit conversion. We start with our negative 1500 kilojoules, and the reason it's negative is because they're still saying that this is releasing the heat, so I'm going to use the negative sign. This is our energy conversion factor. I make sure my units cancel. I convert kilojoules to moles, moles to grams, and it took 30 grams of methane in order to release that much heat. In part C, they want to know what the value of delta S is. Since they didn't give us any entropies of formation, the only way we're going to be able to tackle it is, since we know delta G, and we found delta H in the first step, we should be able to calculate delta S using the Gibbs-Helmholtz equation. I plugged in my delta G value right there. I plugged in the delta H from this first step right there, and I'm going to be solving for delta S. So I'm going to add 800 to both sides, and then I'm going to divide both sides by 298. If I do that, I get 0.03 joules per mole Kelvin. Alright, on to part D, and while I'm labeling it, because I'm going to keep this work here, I'm going to put D over here. So what D is asking is, give an explanation for the size of the entropy change found in part C. So let's go back to part C. They said that we got a positive entropy change, and what that means is that there's more disorder, which we know is favorable for entropy. But you notice how small the magnitude is. I mean, it's almost 0. And so if I want an explanation, we come up here and you'll notice that there are 3 moles of reactants becoming 3 moles of products. There's no change in phase at all either. So I think the reason we're getting such a small magnitude, almost a 0 delta S, is because we are not changing the number of moles of gas, and so we would expect it to be very stable. So here's the description I came up with. Delta S is very close to zero, indicating almost no change in entropy. So I think definitely citing this value is important, and then what did we see up here that would provide evidence for that? So this would be predicted because there are the same number of moles of gas in the reactants and products. So we talked about the reaction a little bit and compared it to that. I think nice and short on this one, shouldn't require much more than that. There are other ways to say it, of course, but making sure that you're talking about this value and you're talking about the reaction.